already seen the last class that it is the consequence of the uncertainty principle, the quantization of energy. There we said that a quantum particle or a quantum system which comprises quantum particles, so the minimum energy cannot be zero. There should be non-zero minimum energy, which is known as ground state energy. Okay. In today's lecture, we are going to discuss about how one can develop the theory for quantum physics. Again, I would like to bring your attention that whatever we are going to discuss, that will be based on qualitative approach. Right? That means we'll play around the de Broglie hypothesis and uncertainty principle, as I said, the two pillars or legs of quantum physics, and try to develop a theory. Okay. So so it must be based on de Broglie hypothesis as well as Heisenberg uncertainty principle. Okay. And as I said, we have already seen the quantization of discrete energy level are the consequence of the uncertainty principle. So as I said, without going deeper, both mathematically treatment as well as historical overview. I mean how one can develop. Let go straight forward a statement which was proposed by Max Born, right? And so the Max Born, he proposed, not proposed, he from his important work he concluded that the quantum physics must be based on probabilistic approach. Or in other words, so in order to develop a theory for quantum physics at elementary level, one need to jump from classical deterministic approach to probabilistic approach. The question here is, what is deterministic approach or classical deterministic approach, and what is probabilistic approach? So once we understand, then we'll see how one can, jumping from deterministic approach to probabilistic approach, one can indeed, develop theory for quantum mechanics or quantum physics. Am I audible?
Yes, sir.
Yes, sir.
So therefore I have asked this question: what is deterministic approach? What is probabilistic approach? So deterministic approach means we can determine precisely all the measurable quantities. When we say measurable quantity, it means position, momentum, kinetic energy, angular momentum, and so on. We will measure with 100% accuracy. For example, if we know the position and momentum at a given instant of time, let's say t equal to t naught, then in the next instant of time, which is t1, we can precisely measure this position and momentum by using Newton's second law. Okay, so that's called deterministic approach or picture. So now we'll see that when we use this deterministic approach, it will no longer consistent with de Broglie hypothesis as well as uncertainty principle. Let's see how. So what does de Broglie hypothesis says? That material particle, if we have a material particle, then there must be de Broglie hypothesis. And if the de Broglie wavelength is associated with material particle, which will be determined by using this relation. And we have already worked out very important problems, some of the important problems. For example, a tennis ball which moves certain velocity and electron which moves certain velocity. And they are by looking by calculated de Broglie hypothesis, so de Broglie wavelength, and by comparing the calculated de Broglie wavelength with the dimension of the particle, we can see whether it is we can apply whether it will show wave nature or not. So that we have already worked out. So in short, it says that a material particle, if you have a material particle, there must be a de Broglie wavelength, which is determined by this. So assuming that the de Broglie wavelength is comparable to the dimension of the particle, that means it will show its wave nature. Okay, so that means wave nature for the quantum particle. Because why we call quantum particle, the de Broglie calculated de Broglie wavelength is comparable to the dimension of the system. So therefore, it's a quantum particle, so wave nature can be determined. So when we say the wave nature is determined, that means it will be it would be decided by the amplitude against wavelength. That means the object will no longer will have geometrical shape, because wave does not have a geometrical space, shape. It spreads over space as well as the time. So it means the particle is no longer geometrical object. But if it's not a geometrical object, and do remember that the deterministic approach, which is Newton's law, is only applicable to geometrical object. That means if you have an object with certain geometry, maybe circular, cylindrical, or spherical, or conical, so or different asymmetric geometry, then one will apply Newton's law and determine the position and momentum. Okay, so now what we see that if it satisfies de Broglie hypothesis, that means if it should be a quantum particle, therefore we should determine its wave nature. So particle is no longer a geometrical object, hence it is not consistent with deterministic approach. Okay, so the de Broglie hypothesis is not consistent with deterministic approach. Then the second one is the uncertainty principle. What does it say? The error in the measurement of the linear position and linear momentum must be h over 4 pi. So let's again impose deterministic approach. If we impose deterministic approach on quantum particle, what does it mean? So it means we can precisely measure both position and momentum with 100% accuracy. That's exactly the deterministic approach says. Okay, so it means there will be error in the measurement of the linear momentum is 0, because we are trying to impose the deterministic approach, that means Newton's law. So when we use delta px is 0, that means px can be determined without error. Then the error in the measurement of the position associated with the quantum particle is infinite. What does it mean? The error in the measurement is infinite. That means particle will be found everywhere. When the error in the measurement is infinite, what does it mean? So particle is spread over position like wave. So particle is no longer a geometrical object. So now, in a simplest, argument, we conclude that when we impose deterministic approach on quantum particle by using de Broglie hypothesis and uncertainty principle, we showed that they are no longer consistent. But the uncertainty principle and de Broglie hypothesis are two legs in quantum physics. Without leaving this or without incorporating these two ideas, one cannot think about quantum theory. So how one can incorporate these two ideas? So these, discrepancies can be ruled out if we think about, probabilistic, kind of measurement rather than the deterministic measurement. Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So now is it clear to everybody? So
Yes,
why,
yes, sir.
how
Yes, sir.
these
Yes, sir.
two ideas, they are not consistent deterministic approach. When we say deterministic approach, that means we again, in a simplest case, simplest level, we think about Newton's second law. Okay. So now So as I said, so this, ambiguity or discrepancies can be ruled out by, if you think about probabilistic approach rather than deterministic approach. The question is how again. So at the end, if somebody will ask you question, so when we study a system, at the end we would like to measure something. That means it could be your position, it could be your momentum, it could be your angular momentum, it could be your kinetic energy, and so on. So these are the measurable quantities we try to measure or obtain from the particular system. So when we'll use it, first thing is that we need to use probabilistic approach. Then the second thing is how we can measure these physical observable quantities. As I said, position, momentum, angular momentum, kinetic energy, and so on. So let's see that. So first we need to, once we use probabilistic approach, what we can say that instead of saying you see, if you look these two things, we use deterministic approach. We said that here, that we can measure precisely the linear momentum, or in other words, we can measure precisely the position if we use deterministic approach. So similarly here, right? So the idea here is that since we are, trying to measure the precise position and linear position or the linear momentum, or here we are trying to, destroy the geometrical properties of the particle. So that means we can not measure both position and momentum with 100% accuracy. So this, discrepancy appears. So it means, so instead of saying the exact or actual position of the particles or the measurable quantities, it could be a position or a linear momentum. Instead of saying it's an exact or actual value, what we can say that the probability of measuring these physical quantities. So what does it mean? That means when we try to measure, as I said, it could be your position, momentum, kinetic energy, and so on. We'll say that the probability of this, measurement, rather than saying the exact or actual measurement. So in that way, what we can say, we will accommodate both de Broglie hypothesis as well as uncertainty principle. Because the uncertainty principle says that we cannot measure with 100% accuracy. So therefore, you can say the probability of the measurement of the quantities. So when we say that means, then we can say at any position, okay, or in position, at any position, or when we do measurement, then it will take some discrete allowed values rather than the sharp defined value. So it means, so let's say the particle we won't find here, we cannot say it, the particle is here, which means the 100% accuracy. That means the probability is 1. What we'll say that here is some probabilities, right? So let's say it's 0.2, and here is 0.4, and here is 0.4, and so we measure in 3 different positions and we say these are the probabilities. Okay, instead of saying the exact value. That means instead of saying the probability is 1, rather than saying 1, we'll have some probabilities at different positions. So then definitely there will be an error in the measurement, because we are not saying that 100% there is a 100% chances that particle will be found here. So there is we say that there is some percentage of that particle will be found here. Okay, so that means there will be definitely some error in the measurement. And so therefore, it does not valid uncertain principle. We say there will be some, error in the measurement, delta x. And as time evolves or as time changes, this probability For example, this case here is 0.2 at time t equal to let's say 1 second, and when time equal to let's say 2 seconds instead of 0.2, here the probability will be 0.4, or some other time it will be 0.1, or and so on. So it means as time changes, this probability will also change. It is not the absolute probability. As time evolves, this will also change. It's like, the wave, which will be, certain amplitude, and this amplitude will change depending on the time. Okay. So it will like this. And this amplitude can be defined in terms of the probability of the finding the particle, or the probability of, probability of the measurement of any physical quantities. Is this clear to everybody?
Sir, can you once again repeat the last statement you said?
Yes, sir.
Okay. So the first thing is the deterministic approach, which says the exact or actual measurement of the physical quantities. What are the physical quantities? Position, momentum, kinetic energy, potential energy, angular momentum. These are measurable physical quantities, and that at the end we would like to know these physical quantities. So the deterministic approach says it is exact or actual value because there will be no error in the measurement. And when we'll impose probabilistic approach, we'll say rather than exact or actual value, there will be some probabilities. Some probabilities at different position with certain allowed values. These probabilities will also change over time, like a wave, whose amplitude changes over time. So the probability will also change over time. Got it? So that way we can accommodate uncertainty principle, because uncertainty principle says that there will be error in the measurement. We cannot measure the these measurable quantities with 100% accuracy. Once we include some probabilities, it means some percentage of the finding particle. So these discrepancies will be ruled out. Got it?
Yes, sir, got it.
So the idea is we have to say that the probability, that means percentage of finding the particles or the any measurable quantities, and these measurable quantities, it is not the fixed value, it will also changes over time. At time change, this relative probability will also change. So then the question is that how we can incorporate these changes. This probability will also evolve over time, and that can be achieved, as I said, by using the wave function, right? So the wave function and the amplitude of the wave function at different position will decide the magnitude or the probability of the finding the measurable quantities. So when I say measurable quantities, any one of these variables, momentum, kinetic energy, and so on. Okay. So and then you might ask question that the wave function we are talking here, is it the same wave function that we have already seen diffraction, interference, and even in wave chapter, or in general in optics? No. So this is not the same wave functions. So in which sense? So this is a different than the wave function that we have already seen in optics chapter. So let's discuss that one. The first thing is that in a classical physics, when we say classical physics, that means the deterministic approach. It means the Newton's law is applicable. So the only thing we need to know the position and the linear momentum at a given instant of time, and by using Newton's law, you can determine in the next instant of time. For example, when someone is trying to know what would be the position and its momentum at say nth time Tn can be precisely measured by using these initial conditions. So you can see this dot, right, red dots. So this represents like time equal to T1, T2, T3 and so on. So by doing this iterative method, one can determine what would be the position and momentum at any arbitrary time Tn. And if you join these points, then you will get a path that is called the trajectory. And the coordinate x and px is known as the phase space. So if you join position and momentum that we measure or we calculate at any instant of time, then it will trace a trajectory. That's called trajectory. And since in its phase space, because this is called phase space x and px, so therefore a trajectory in the phase space. In short, so the trajectory in the phase space contains all the information of the classical particles, right? If somebody will ask question, what is the position and linear momentum, let's say 10 seconds, you can say, look, so this is the state, okay? So then, and from this trajectory, you can get the information, okay? So similarly, the wave function is like in a trajectory in a phase space. So wave function contains all the information of the quantum particle. Got it? So in short, the trajectory in the phase space contains all the information of the classical particles, and wave function similarly contains all the information of the quantum particles. So if somebody wants to know any of the measurable quantities, for example, position, momentum, energy, then the wave function will give these informations. Okay, is it clear? So whatever I have said, I have written down here. Am I audible?
Yes, sir.
Yes, sir.
So whatever I have said, I have written down here. You can read it out. So now, this is the comparison between the trajectory in phase space and wave function in quantum systems. So we'll also discuss in great detail later on. So let's jump into how this quantum wave function, the wave function that are associated with the quantum particle, which will explain the probabilistic approach, or through which probabilistic approach can be incorporated, right? So this wave function, how it differs from the the normal wave function that we have seen in the optics chapter. So the representation is exactly same, like in complex form this, and in one dimension like this, the same representation as the standard wave function that we have seen in optics chapter. If you remember, a sin k dot r minus omega t, or a e to the power I k dot r minus omega t. However, the properties of the quantum mechanical wave function differs, or it is not the same as the optics wave function. So in optics chapter wave function, what we'll have? The amplitude and frequency that decides everything. That means the kinetic energy and intensity and so on. For example, the amplitude will decide the intensity associated with the wave, and the intensity, as well as then the frequency will decide the energy associated with the wave and so on. So here, so this parameter, they represent something differently, that we'll see. So first of all, that the wave function, the quantum mechanical wave function should be single valued, and then it must be finite. That means it should not be infinite. It should be finite. We'll discuss, okay, in great detail what does it means. And then it must be square integrable. What does it means? So it means if you integrate this wave function with its complex conjugate, psi star represents the complex conjugate. So therefore psi mod square equal to the psi star psi x, where psi star is the complex conjugate to psi. So that is represented by different symbol rho, right? So that is called probability density. That means the probability per unit volume. And here, since we are talking in the context of one-dimensional wave function, for simplicity, so therefore the probability density will be probability per unit length. So in short, the psi mod square, which is psi star psi x, where psi star is the complex conjugate to the psi x, which is nothing but the rho. So that means if we integrate rho dx, that will be 1. Minus infinite means. Okay. So that is called the square integrable. Or in general, in mathematical language, if a function, if fx is a function, if we take the mod square dx minus infinity to infinity, if it is not infinite, if it is a finite, then it's called square integrable function. It means a function is called a square integrable if it does not goes to infinite, if the mod function square dx over all the integrals. So this case it is 1. Why? Because if this represents the probability of the measurement of any physical quantities rho, that means finding all over the space minus infinity to plus infinity is 1. So it makes sense, right? That means if we are considering finding the position of the particle, that means if we source, minus infinity to plus infinity, that means whole space in, one dimension, then the total probability will be 1. Got it? Yes or no?
Yes, sir.
Yes, sir.
So in
Yes, sir.
short, it must be single valued, it must be finite, it must be square integrable. And then the fourth property is that this wave function must be continuous at all places, including boundaries. Not only this, the wave function, it's the first derivative which must be also continuous. So what does it mean? So if we have two media, let's say medium 1 and medium 2, and if let's say wave function is like this, so x equal to a is the interface, right? So it means the x equal to a is the boundary. So that means the wave function at the first region at x equal to a must equal to the wave function on the second x equal to a. The first derivative also this. So therefore, the psi x and its first derivative, that wave function and first derivative with respect to cosinus, is continuous all places including boundaries. And the last, properties of this quantum function wave function, quantum mechanical wave function, that it should satisfy Schrodinger equation. How many of you have heard about Schrodinger equation? Anybody? Have you heard about Schrodinger equation before? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, and so these are, 6 important, properties or the characteristic. You can say the properties associated with the wave function, or you can say the characteristics of the wave function. So in that sense, the quantum mechanical wave function differs the wave function that we have seen in optics chapter. Okay, so let's see, right? So let's see what does it mean, right? The single valued, finite, square integrable, and so on. So here I have shown some represented wave function. So psi x at x, that means at a given instant of time, let's say t equal to 1, because it is the only function of position. So do remember that wave function is function of position as well as time. The second order differential equation that we'll see, right? So at a instant of time, so therefore it is independent of t. So this is the wave function with respect to the position. Okay. So if I'll ask question, is it a valid wave function? Then definitely say no. Why? Because at x equal to x naught, it is not finite. This double-headed arrow says that they diverge towards infinite. It is not finite at x equal to x naught, as well as it is not continuous at x equal to x naught. So therefore, it is not a valid wave function. And let's look at the second one. So now, so this is not also a valid wave function, because why? It is not a single valued, because at x equal to x naught, it is a dual valued function or multi-valued function. So it is not a single value. So therefore, it is not a valid wave function. And then the third one, at x equal to x naught, it is not continuous. It is a discontinuous function. Yes or no? So therefore,
Yes, sir.
this one is
Yes,
not a valid wave function. And the fourth one, of course, it is a valid wave function because it is single valued. It satisfies all the properties of the wave function. So similarly here, some other function, for example, here, at x equal to x naught, the first derivative is not continuous. So therefore, it is not a valid wave function. So this one, yes, it is a valid wave function. So this one, no, it is at x equal to x naught. It's a tri-valued function, 3 values. So therefore, it is not a single value. So this one is valid wave function. And if you remember, so this is the damped harmonic oscillator motion. So the damped harmonic oscillator motion, the plot of the position with respect to time, you can say is you can say is one of the valid quantum mechanical wave function plot. This one is a valid wave function. This is not valid because it is not continuous. This is valid. This is also valid wave functions. Okay. So now from this graphical representation of the wave function at a given instant of time, let's say t equal to 0 second, we now conclude that which of them will be valid wave function and which of them will not be valid function with appropriate regimes. So in your exam, if I'll ask a question or show some representative plots and ask them whether they are valid wave function or not, you can easily figure out whether they are valid wave function or not with appropriate explanation. Okay. So this is all about quantum mechanical wave function, and at the end, so what we conclude that it should satisfy Schrodinger equation. Then you might be wondering, although some of you know, or all of you know about Schrodinger equation more or less, but you might be wondering um, what is it actually carry, what kind of information this Schrodinger equation carry, and how it explain or how one can get measurable quantities such as position, momentum, energy, and so on from this wave function, and how the Schrodinger equation plays an important role to get this information from the wave function. So that we'll discuss in the next class. Any question? Any question? So if there is no question, it indicates two things. It means you understood everything or other way around. So I hope the first one is correct. That means you have understood everything. So if I'll ask you a summary of today's lecture, what would be the summary of today's lecture? 5 important, points or keynote. The first thing is that we said that one needs to jump from deterministic approach to probabilistic approach as proposed by Max Born. And then we said why we need to jump from the probabilistic approach. Then we said in order to incorporate probabilistic approach, we have to talk about, percentage of the finding of measurable quantities. Okay, or probability of finding the measurable quantities. Certain probabilities rather than saying the exact or sharp defined values. And then we said that this percentage of finding these measurable quantities, because at the end we are interested to know about these measurable quantities, position, momentum, energy, and so on. So we said that in order to incorporate or in order to understand percentage of finding this measurable quantities or probabilities of these measurable quantities, we have to deal with wave function. And then we said, what is wave function? Wave function carries all the information of the quantum particle, like trajectory in phase space for classical particle. We talked about what is trajectory in the phase space. That means the position, momentum, pair at all time. If you join, we'll get a trajectory in x and px space. So wave function comprises all the information of the quantum particle, like trajectory in the phase space for classical particles. Then we said the representation of the quantum mechanical wave function is exactly same of the standard wave function that we have seen in the optics chapter. However, the properties associated with the quantum mechanical wave function is different than the standard wave function that we have seen in optics. Like the wave function must be single valued, it must be finite, it must be square integrable. The third one is the wave function should be continuous. The fifth one is the first derivative should be continuous at all places, including boundaries. And the sixth important properties associated with the wave function is it should satisfy Schrodinger equation. Right? And but our intention is how one can get the measurable quantities from this wave function. And in the next class, we'll see like Newton's second law in classical physics gives the information. That means if you know position momentum, by using the Newton's second law, we can determine the position and momentum in the next instant of time. And therefore, you will get the trajectory. So similarly, the Schrodinger equation, by using the Schrodinger equation, one can get information from the wave function. Like classical physics, the Newton's second law using on trajectory in phase space, we'll get information. Similarly, by using the Schrodinger equation on wave function, we'll get the measurable quantities with their certain probabilities. So the Schrodinger equation is very important in quantum physics. So that we'll discuss in the next class. So is this clear? The summary of on today's lecture?
Yes, sir.
Yes, sir.
So no question, right? So I hope all of you are doing the assignments and submit the assignment on time. And you have already seen, right? So in your exam, there are some problems based on your assignments. Okay, so it is important to solve all the assignment problems. In your end sem, you will also find similar type of problem in your exam. Okay.
Yes, sir.
Yes, sir.
Yes, sir.
So if there is no question, I think we should stop here and we'll meet in the next class to discuss about the Schrodinger equation, and we'll see how by applying Schrodinger equation on wave function we'll get the probability of the measurable quantity. That we'll discuss in the next class. Bye everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.